Hi, leader Sasha Asinovsky. Today we're going to look at this problem, number 83 from, I believe, chapter 5 of Unit 2. We're going to be talking about a charge distributed on a line charge, and its effects on point P purely in terms of electric field. Okay, the first thing I said is purely in terms of electric field, which sounds kind of like a weird sentence, but essentially what I'm trying to say when I say that is, first, let's look at point P. There is a point there, it's P, a point located in space, but there is nothing for the electric field emanating from this line charge to act on, right? The same way as if I look at planet Earth, we have the gravitational field going down to planet Earth, very crudely drawn. But unless I actually insert a mass, let's say I put a point mass in there of 10 kilograms, the force of gravity is going to be 10 kilograms times the acceleration due to gravity is equal to something in newtons. Unless I put something into the field that the field can act on, there won't be any force. So the first thing that I don't want anybody to confuse here is there will not be any force at point P. There is no charge there for the electric field to act on. There is simply a point located in space and an electric field emanating from this line charge that will pass through P. It's not going to affect anything. Okay. So we have to look at a few things here. The charge per unit length on the thin rod shown below is lambda. Lambda just means, okay, I have this section of rod, and for each section on this rod, I'm going to have some amount of charge. Now, the whole line, let's say it contains charge Q. Let's say it's 20 coulombs. And let's say the length of the entire section is 10 meters. If I want to know how many coulombs of charge sit in every individual meter, let's say this is 1 meter and the whole length is 10 meters. How much charge is stored per unit or per meter? I say, okay, 20 coulombs divided across 10 meters gives me 2 coulombs that I have for every meter of this line. And that's what lambda is. And I know that for some of you that might be pretty obvious. For some of you it might not be. For me, when I was taking this course, I was wondering, why are we using Greek letters? This stuff is starting to really bother me. So everyone's in a different place, but it's pretty important to understand the purpose of lambda. Because when we look at the equation for an electric field, E is equal to kq over r squared, this is talking about Q, where Q is a point charge, right? We have a proton floating in space. It's going to emanate electric fields, field lines pointing away, positive test charge. And the point is, the electric field measured here, or here, or here, are going to be functions of distance from this proton and the magnitude of that charge. The stronger your charge, or rather the higher your charge, the stronger the electric field. The further you get away from the proton or the charged particle, the lower or the weaker the electric field. And that operates on the inverse square law. So same deal as gravity, right? G mass 1 mass 2 over x squared r squared, where x, r, whatever you want to define it as, are the distance between the two masses. So the field and the strength of the field is going to fall off pretty quickly. So what's the point I'm trying to make? Well, for this problem, when I look at a charged line with some lambda, I'm going to know that for each section of this line charge, let's say I pick this, and this is L over 4, if I want to know the amount of charge stored in that section, and I know the amount of charge stored in this section is Q over L equals lambda. So the total charge over the total length is your charge per unit length. And I want to know how much charge is in a fourth of that line. Then I take, okay, well, length divided by 4 times lambda. Why do I do that? Because, watch this, any section of the charge line that I take is going to be measured in units of meter, right? Like I pick this or I pick that, that's meters. It's a distance across this line going like that. So when I'm asking you, I'm asking you, the student, I'm saying, how much charge is in something? You should think coulombs. I'm asking you purely for how many coulombs of charge are in something or somewhere. So when I take that quarter, 1/4 L, and multiply by lambda, I'm really saying 1/4 L times the total charge, well, Q total over L. Well, my L's are going to cancel, aren't they? My unit of meters is going to cancel, and I'm left with 1/4 of the total charge. In other words, that's the same as me saying I have a line that stores a charge. I'm going to take a fourth of that line. So therefore, a fourth of that charge must be stored in that section I took. And it sounds pretty intuitive, but it's important to understand the purpose of lambda before we continue here. All right, so the next thing we want to look at is the big bad hint we get here. Solve this problem by first considering the electric field dE at point P due to a small segment dx of the rod. This is a helpful hint, but I think the notation from calculus and really calculus as a whole can be a little intimidating in this course, but just view it as a tool that's going to help you find the electric field that you're looking for. Because it would be a lot different for me to say, okay, instead of a line charge, let's look at 5 charged particles sitting across some length. Then I know that if we have a distance from here to here of A, and we have a point here, and this is where I'm measuring the electric field, well, I'm going to say that the electric field at point P is going to be this sum from n equals 1 to 5. I have 5 charges sitting here of kq over r squared, and then we say n r hat. The reason I dropped those n's in there is because, okay, let's label this charge as charge 1, 2, 3, 4, 5. This symbol just says I'm adding up all of the electric fields from every single one of these points, or every single one of these charges, onto point P. The way I'm going to do that is say, okay, I have an electric field due to this point charge, and it's going to be it's going to be affected by the magnitude of this charge, and it's going to be affected by the distance away from point P to that charge. Okay, so that's our first thing. So k q naught over r squared naught, and in the context of this problem, if we have the distance a between the two, it's just going to be k q naught over a squared. Then we move over here to the left to the next charge, and we want to include that in our sum for the electric field. So we say, okay, let's call this distance d, right? We want to find the electric field due to that second charge. So we say kq, I labeled it as 2 up there, so I'm going to just use 2 here. kq2 over r squared, r2 squared. And that, according to this problem, is a distance of a plus that d, the distance between these two, plus the distance between that and the point. That's going to be my total distance between the point and this charge. Because really, what am I asking? I'm asking for the electric field due to this point on this charge. And I'm doing that from this point to this point, this point, this point, and this point. So I'm adding up a bunch of electric fields for 5 different points. Obviously, that's not what I'm doing. Well, that's not literally what I'm doing when we look at this problem. Because when we look at this problem, you can think of it as an infinite amount of infinitesimally slim sections of this rod. Now, let's say I take a portion of this rod to be, well, first let's say this is the x-axis, extending out that way, right? And let's say that left is positive in this case, so we're going to say positive. As I go along the x-axis, I can pick a slim sliver of this rod. Let's call it a width of dx. The amount of charge in that little section I picked is going to be, remember, lambda times some length gives me charge. So dq, the tiny, tiny amount stored in that tiny, tiny section of line, is going to be lambda dx. Okay, well, what's the next part then? And by the way, that's in the hint too. Well, integrating dE over the length of the rod. So we have a few things to consider here. When we make an integral, we have to select bounds, we have to select a variable to integrate over, and we have to figure out what's in the integrand. Okay. I want to take us back to Calc 1 for a second, and I also want to look at that example I drew earlier. We had these 5 point charges that add up, and you can just add their fields up at point P as n equals 1 to 5, this being 1 dot 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 5, and you use the equation E, okay? In Calc 1, we talk about, okay, what if I have a integral, or what if I have a summation going from n equals whatever to infinity? That's an integration, right? I'm saying that this line charge is essentially the same thing as an infinite amount of tiny pockets of charge that are all going to add up to some net electric field going through point P. Okay, so in that vein, the first thing we want to decide is what's changing? What is changing? Because ultimately with an integral, something is changing. Otherwise we wouldn't be integrating to begin with. Well, if we look carefully at the problem, as we find the electric field due to this charge section, and this charge section, and this charge section, and this charge section, all of them differ from each other because the distance from here is some distance. This distance from here is some other distance. And then yet from here, there's another distance. So what's really changing as you add up all of the little contributions of electric field to the field on P is the distance of the section of charge contributing to that electric field. The same way, again, as if I refer to this system of 5 charges, all producing an electric field going through R, or through P, I'm sorry. The field due to this charge, well, it's going to be a little stronger because this charge is the closest to P. And the field due to this charge right here in the middle is going to be a little weaker because even though the magnitude of this charge, Q, is the same as this charge, Q, let's just assume they are, this one's further away. And if I have something that has a magnitude dropping off by a factor of 1 over r squared, then this is going to be a lot weaker in terms of electric field than this. So ultimately, that's what's happening. That's what's changing throughout this problem. As you integrate through this entire line, the location that you're taking the electric field from, and remember each sliver contributes a little bit of electric field, the location is changing. The distance in the formula kq over r squared is changing. So how do I account for that? Well, we're taking the integral, so let's start by setting the bounds. How do I account for the fact that the distance is changing? We start by incorporating the first distance, right? Because remember, the electric field is kq over r squared, and that's for a point charge, I know, but in this case, just let q be charge as a generalization for a second. R is the distance. The first amount of field on P, there's nothing between P and this line charge. There's nothing here along this section that's going to contribute any amount of electric field to P. So it's just a big empty space. Meaning, if I want to make an integral that represents contributions of electric field, I have nothing going on in this section of A. Rather, A is the distance between P and the first bit of this line charge that's going to emanate an electric field. So that first sliver that we're going to use, which is why the first bound you want to set is A on the bottom, right? Your electric field contributions aren't going to start here or here. They're going to start here at a distance A. So at a distance A, you could also think of it as the first little piece of charge, or the first little sliver of the integral that we're doing is contributing the electric field. Okay? Now, obviously, well, as you go through this line charge, you're going through a distance L. So let's say we're looking at this point now. What does the electric field do to that point? Let's say it's a point charge. It's going to be KQ over that distance A plus the length of this entire segment. All the way at the end now, we have a distance away from P of L plus A, which means that we certainly want the distance in the denominator to be L plus A squared, and the r hat is just notation. Okay, so we want to integrate until L plus A. Why? Because if the integral is saying, okay, we're contributing a bunch of pieces of charges that are contributing an electric field to P, well, the very last piece of that is going to be right here at the end of this line, okay? Next, we look at dq is equal to lambda dx. So earlier I was talking about, okay, well, this little sliver of this line is going to have some charge denoted by dq, which is a function of the linear charge density times the little sliver of distance you pick. The same way as if I pick a fourth of this line, 1/4 L is going to contain 1/4 of the entire charge in that segment. Same with a tenth, same with a hundredth. So if I'm looking at a very, very, very tiny section of charge, dq, then dx, where dx is the length along the x-axis, and lambda is the amount of charge for this entire line, well, dx in meters and coulombs per meter, the meters are going to cancel. You're just going to get some little tiny amount of charge for some little tiny sliver that you draw. Which is why, instead of Q, you're saying, okay, for every little section here, dx, 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 the charge contained in each of these is going to be lambda dx. Which is why when I go to my integrand, the function for electric field is E is equal to KQ over R squared. Q, which refers to charge, in this case, my charge in each sliver is going to be lambda dx. So I say lambda dx, right? K is a constant. We're just pulling that over from the equation. And R squared, and this is the important part, R squared is what's changing. Now, a slight hiccup that can happen here is, as you can see, the people writing the problem chose to just treat it as dx. Well, you're thinking, okay, how am I going to put r into this problem if I'm integrating with respect to dx? Well, the answer is r. Remember, r is a horizontal distance from, r is the distance away from P to the little sliver of charge that you're measuring the electric field from, right? So don't let that confuse you too much. On the x-axis that we drew, r is just going to be, okay, this distance from here to here. So really, you could say, okay, we're integrating through the x, and in this case, the denominator is going to be the horizontal distance from P to every sliver is going to be x squared. And you're thinking, where'd the r go? This is r. This is going to be our distance from every point on this line to P. And when you actually evaluate this integral, you're going to see that you're evaluating it by plugging in the bound values into whatever we get. So immediately we see this and we're like, okay, k and lambda are constants. So we say k lambda a L plus a dx over x squared. And from here, we have some Calc 1 stuff. So just in case you forget the integration, we say, okay, k lambda, and we say that's really the integral a L plus a of x to the minus 2 dx. And then as procedure calls for an integral, we say, okay, plus 1 over whatever that is in the denominator. So we say k lambda 1 over x, that becomes x to the negative 1 over negative 1, which is a little strange looking, so we can rewrite it as k lambda x to the negative 1 over negative 1 evaluated from a to L plus a. Then we say, okay, that's just negative k lambda over x evaluated from a to L plus a, which then becomes negative k lambda 1 over L plus a minus 1 over a. Now, looking at the book, we can see that seems pretty consistent with the answer. We have k, which is 1 over 4 pi epsilon naught times lambda times that expression, which we appear to have right here. So that's the conclusion. Now, the only other hang up here is the sign. What is the sign going to be due to the charged line? Well, we don't know. We are given a charge per unit length, but we're not told if this is positive or negative. So really, it just depends. If it's a positively charged line charge, then the direction of the field lines is going to be to the right. And if we say that our x-axis that way is negative and this is positive, as we described above earlier, then negative. And if it's a negative charge, then the field lines will go that way and it'll be in the positive x direction with that notation, just keeping consistent. So really don't worry about the sign. We're looking at a magnitude, and the sign is decided by what type of charge, positive or negative, you have on the line charge. But this is the same as writing that answer. 1 over 4 pi epsilon naught lambda 1 over L plus a minus 1 over a. So that's that problem. It's a little weird, but if anyone has further questions, please let me know.